Hello everyone, my name is Peng. I come from Fudan University, China. It's my honor to be here to give this talk. My paper topic is assessing code clone harmfulness, indicators, factors, and countermeasures. Here is 4 parts of my presentation. The first part is motivation. The second one is concept model and approach. The third is empirical study, and the last is contribution. Previous studies have found that about 19% of source codes of Windows are code clones. 15 to 25% source code of Linux kernel are code clones. In open source systems, up to 50% of source code are code clones. Code clones are more or less harmful to the software project. Are all of them equally harmful to the software? In this paper, we design a model to study this research question. Code clones come from 2 aspects, bug propagation and consistent change. Suppose there is a code fragment which contains bugs. The code fragment was copied and reused at revision 2, forming a clone group that all the instances contain bugs. Then, the bug was fixed in the same way later in one commit, so they remain code clone in revision 3. In another situation, there exists a clone group. Instance 2 changed at revision 2 for a new function request. The developer found that instance 1 also needs the same change, so he modified it. These 2 codes, changed in the same way, we call it consistent change. In this paper, we mainly focused on consistent change, studying the harmfulness level related to consistent change. The harmfulness of a clone group is determined using assessment rules defined with 4 indicators. Clone harmfulness is represented in 4 levels. Then, we studied factors which can influence the harmfulness of clone group. Finally, we tried to explore possible technical and managerial countermeasures by monitoring the factors to mitigate clone harmfulness. As to consistent change, there are 5 different modes. The first one is that clone instances in a clone group never change. In another situation, clone instances in a group change separately. The third is that clone instances always consistently change with no time delay. Another one is that clone instances in a clone group consistently changed, but they didn't change in the same commit operation. The last one is that clone instances in a clone group changed consistently with a time delay. At the same time, the message of the commit operation shows that there is a bug fix operation. On finding all the consistent change modes, we proposed 4 indicators which can be used to describe different consistent change modes. The first one is changes per instance. It is defined as the count of changes to clone instances divided by the count of clone instances of the clone group. For example, the clone group contains 2 instances. The instances changed 4 times in the evolution history, so changes per instance equals 2. The second indicator is consistent change ratio. It is defined as the percentage of the count of consistent change over the total count of all changes in the evolution history. For example, there are 4 changes. Suppose that the clone pair consistently changed at revision 2. Then, the left instance changed at revision 3. The right one changed consistently at revision 4. So the 4 changes are all consistent change. Thus, consistent change ratio equals 1. The third indicator is consistent change latency. It is defined as the mean value of all consistent change latency between any 2 consistent change pairs. In this example, the first consistent change pair appear in the same commit. The second consistent change have a 3 days latency. Thus, consistent change latency equals 1.5 days. The fourth indicator is existence of late consistent change related bug fix. which can be collected from the commit messages of the late consistent change. Then, we design a clone harmfulness assessment model for a given clone group. If the values of the change per instance equals 0, then it is regarded as harmless clone. If the value of change per instance is bigger than 0 and the value of consistent change ratio equals 0, then it is harmless. If the value of changes per instance is bigger than 0 and consistent change ratio is bigger than 0 and consistent change latency equals 0, its harmfulness level is low. If a clone group experiences consistent change in its evolution, there exists consistent change latency and no bug-fix information can be found. We regard it as medium-level harmfulness. If there exists bug-fix commit, we regard it as high-level harmfulness. Here is an example from Redis. The clone group contains 2 instances. When the function is over, the dynamic storage of the declared variable cpy needs to be released. But in this code, the developer freed a wrong object ap, and this defect was propagated from clone instance 1 to clone instance 2. Later, a developer found the defect and modified the wrong code, but he ignored clone instance 2. About 7 months later, another developer modified instance 2 consistently. By the assessment model, we regard the harmfulness of this clone group to be high. For extracting a clone harmfulness indicators, we designed a new genealogy extractor based on the Git strategy. In Git, if a file is not changed through several revisions, then there only exists one blob object for this file. In this example, only 7 files for code clone detection by our new approach. Once the clone detection is done, we can recover the unchanged code fragments by the revision information. By traditional approach, one needs to detect code clone from 17 files. By this way, we can reduce the code clone detection time, thus accelerating the genealogy construction procedure. Then, we did an empirical study. We first studied the distributions of the values of the harmfulness indicators. Then, we studied the distributions of the clone harmfulness levels. Once getting the harmfulness level, we discussed it with professional developers to confirm the harmfulness of the assessment model. We also studied the relationship between the harmfulness factors and the harmfulness levels. At last, we investigated what countermeasures can be used to mitigate the harmfulness of clones. How acceptable are they by software professionals? We selected 5 famous open-source systems and 3 industry systems. These systems were written in 3 different languages. Each of the open-source systems has more than 10 years of history. The latest revision of systems contains 200,000 to 26.1 million lines of code. We collect software systems with different languages, different revisions counts, and different files, making our results more convincing. Here is the result of research question 1. For change per instance, 52 to 73% of clone groups are not changed. 74 to 92% clone groups have been changed no more than once per instance. The percentage rises up to 86 to 98% when considering clone groups that have changed no more than twice. Cumulative curves typically jump at integer values. For the consistent change ratio, 20 to 59% of clone groups do not experience any consistent change. 38 to 75% of clone groups change consistently all the time. For consistent change latency, the curves of the systems are not similar with each other. This may result from different development patterns of different systems. Table here shows the harmfulness levels of the subject systems. Over 60% clone groups are harmfulness. 11 to 34% of clone groups are of low harmfulness levels. Most systems have less than 3.2% medium level harmfulness clones and less than 4.1% high level harmful clones, except for Project C. Among the harmful clones, all systems have more low harmful clones than medium harmful clones, except for Project C. Then we organized a half-day seminar meeting with 6 professionals. Industry developers tend to agree on harmfulness and lower level harmful clones. They think some of the medium or high harmful clones are sometimes not so bad because of the use of automatic code check tools used by different teams. Then we studied 3 possible factors which may influence the clone harmfulness. The first one is locality of clone instance. Each project has 3 stack bars from the left to the right. The stack bars represent clone groups that clone instances reside in the same file, in the same directory, and across multiple directories respectively. We observe significantly lower percentage of low harmful level for clone group across multiple directories than for clone group within the same file or within the same directory. The second factor is size of a clone group. The left sidebar represents the percentages of harmfulness levels of clone groups with 2 instances, the middle with 3 to 4 instances, the right with 5 or more instances. There is no evidence that the size of clone group is strongly related to the harmfulness levels. The third factor is number of collaborating developers. The left sidebar represents the percentage of harmfulness levels of clones maintained by single developer, while the right by multiple developers. Our results show that clones maintained by multiple developers have comparatively higher percentage of medium or high harmfulness levels than those maintained by single developers. At last, several countermeasures which could be used to mitigate the harmfulness of clones was proposed. For each factor, we give direct and indirect countermeasures. Direct countermeasures change the corresponding factors directly, while indirect countermeasures do not change the factors but providing guidelines for developers to follow. Then we discussed it with professional developers. They give 3 feedbacks. Moving clone instances from scattered directories into one single directory is good practice, but we do not suggest put them in one file. We have utility methods for routine work, such as output debug messages, but they still have medium harmfulness level. Although reassigning work to the same person is not always possible, we are reorganizing our teams for various purposes, including arranging the same person in similar source code or product features. The contributions of this work are as follows. We proposed an approach for assessing the harmfulness levels of code clones. We studied several factors that affect the harmfulness of clones. We did a large-scale empirical study about clone harmfulness. Finally, possible countermeasures to mitigate clone harmfulness was given. That's all. Thank you.